So today our topic is enthalpy of vaporization. I told you we have two-phase system. The first topic was Maxwell question. The second one, the residual property, and the third one is the two-phase system. So in two-phase system, we will study the enthalpy of vaporization. Like it will be represented by delta HLV. It's also called latent heat of vaporization. So you remember we discussed already uh, actual enthalpy, like H is equal to Hi naught plus Cp T minus T naught plus Hr. So this is the actual enthalpy and this one is the residual enthalpy. So and then we discuss all the change in enthalpy. And that one is delta H equal to Cp T2 minus T1 plus H2R minus H1R. So we can this one. So it can be so we discuss this so many different cases. Sometimes if state 1 is ideal, then H1R is you can eliminate. If there is second state is ideal, then you no need to find H2R. If it is isothermal, then no need to calculate Cp because Cp is a function of temperature. So this is how we can play with this question and we can have so many cases. So we discuss only actual enthalpy, residual enthalpy, change in enthalpy. So today the fourth one is enthalpy of vaporization or latent heat of vaporization. So again we take the help of Gibbs energy. So only Gibbs energy is a property that is zero at equilibrium. Why? Because this is the only property that is equal to zero, because this is the only property which is the function of temperature and pressure. Remember, chapter 6 in the beginning we discussed Gibbs energy is a function of temperature and pressure. So uh, and so you can say at equilibrium at constant temperature and pressure, the Gibbs energy, change in Gibbs energy is zero. So already the question is the dg is equal to vdp minus sdt. So what we can do is we can write down for two phases, like in dome. So we have VLE here, two phase. So we have vapor and we have liquid over here. So vapor and liquid, and both are at equilibrium. So what we need to do is the all calculation will be based on PSAT under this dome. So what we need to do is we can change this question. So we can write down for vapor phase, we can write down dgv equal to vv you can dp sat minus sv dt. So similarly for liquid phase, we can write down vl dp sat minus sl dt. So what we can do is at equilibrium, we can equate both 0. He said SLDT. So what we can do is we can take the V term together or dp sat term together and dt term together. So it will be like you can say here Vv minus Vl dp sat equal to Sv minus Sl dt. So we can write down this Vv into delta VLV dp sat, and this is delta SLV dt. So we can write down dp sat over dt equal to delta SLV over delta LV. So where delta SLV, entropy of vaporization. So where you can say delta GLV also delta HLV minus TSLV. So if you so you know at equilibrium this is again 0. You can also get it from here, and it will be this is second law of thermodynamics. So it will be delta SLV equal to delta HLV over T. So we can plug in this value over here. So it will be dp sat over dt equal to delta HLV over T delta VLV. So this is called enthalpy of vaporization. And this question is called Clausius-Clapeyron question. This is called Clapeyron question. So this is the exact question. This is also called exact question, as it has no assumption. So there are so many questions there to find the enthalpy of vaporization. Maybe you have already studied in chapter 4, like other enthalpy of vaporization, other questions. For delta HLV, one is called Troughton rule. The second one is Riddle rule. Third one is Watson rule. So these are all, like in this one is chapter 10, chapter 4, 4.12 question number. This one is 4.13. So this one is you can see over there delta Hn over Rtn equal to 10. So this is very But in your course we have only because these questions you have already discussed in maybe Chang 313, Chang 211. So we will not discuss it. So our goal is to discuss only class Clapeyron question, and this is the exact question with no assumption. This is the most accurate question for calculating the enthalpy of vaporization or entropy of vaporization. So if we make this question some assumption, so there is one more author joined with this guy, and he make this question more simple. That question is called Clausius-Clapeyron. So Clausius-Clapeyron, same. So Clapeyron is there. So there is one more author called Clausius. So they made three basic assumptions, simple assumptions. They assume that you see here delta VLV. I forgot. I did mistake over here. So you see over here, so delta VLV equal to VV minus VL. So the class in this question, they assume the volume of vapor is very large compared to volume of liquid. So it shows your delta VLV equal to VV. So we are ignoring this part because once you calculate this value will come in thousands, and this value will come in tens or hundreds. So this value is very small, but because Clapeyron question is exact question, so they don't ignore any of the factor, but any of the any of the term. But in Clausius-Clapeyron they try to make it more easy, but this question is for low pressure. If pressure is very low, then they apply because we are saying based on the second assumption. So this is the first assumption, that the volume of vapor is very large compared to the volume of liquid, so your delta VLV equal to the VV. The second assumption is, so these are the assumptions. So the second assumption is the volume of vapor is behaving as ideal gas, RT over P sat. So no need to calculate Z. The third assumption is Z means compressibility factor. The third assumption is your delta H LV remains constant. Throughout T. So this is the third assumption. So based on these assumptions, we can have another question, and that one is the Clausius-Clapeyron. So if we plug in these values like RT or P sat over here, so here we can plug in the value VV, and then we can plug in, so like we can have dP sat over dt equal to delta HLV over T. So instead of this one, we plug in VV, then instead of VV we can plug in RT over P sat. So once we can do, then we can just factorize. You can see here it will ln P sat will be over here, or P sat will be over here, and we can write down this one as delta HLV over R dt over, so this dt over T square. So we can write down this question in another form, dP sat you can write down in terms of I forgot to, so d ln p set, because if you can take the differential it will be 1 over p into dp, so it will be same r, so we can write down d, because if you take the differential of 1 over t you will get this form 1 over t square. So we can have, and there will be minus sign of course, because it will be minus 1, then it will go down. So if you differentiate this 1 over t you will get this same. So this is the another form, or you can say dp ln p set over d1 over t equal to delta HLV over R. So this is y is equal to x. Okay, so this is the y is equal to, so this is y is equal to mx. So it means there is no intercept. So this is the slope of the line. Like if you can draw a line 1 over t versus ln p, you will get a straight line. So the slope of the line is will give you delta HLV over R, from where you can calculate the because in this case we need a lot of data points so that you can plot and get the, I'm just giving you idea because in exam, in maybe once you go to higher class next semester, you will use this concept and you will do the experiment, and then you will plot the graph of 1 over t versus ln p. You will get a straight line. From the line you can get the enthalpy of vaporization of the water. So that's why I am giving you the, so the slope of the line will give you the enthalpy of vaporization. Similarly, if you want to write the Clapeyron question, so if you want to write the Clapeyron question, then it has the almost same form. So it will only difference is so if you plot the graph 1 over t versus ln p set, then your so I'm not going detail to drive how we can drive this question, but you can see this question is over there. So this is the difference between, so this is for Clausius Clapeyron and this is for the Clapeyron question. So I'm just giving, this is only for your next semester, we no need to do here, because we will not solve the problem by giving graph, we give me data and you can solve the problem. Okay, so if you integrate this question, if we integrate this question, so what I can do here, so I can integrate from t1 to t2. So integrate, if we integrate this question, then we can come up with, so integrate from p1 to you can say integrate this one, it will be more easy. Then from t1 to t2 and p1 to p2, you will get p2 and p1 set equal to delta HLV over R 1 over t1 t2. So this question you have to use the box one. So there are two questions that you need to find the problem, like this one, the Clapeyron question and the Clausius Clapeyron question. So I can write over here. So the final questions are Clapeyron, the Clapeyron question is dp set over dt equal to delta HLV over T delta VLV. And we have Clausius-Clapeyron. And that one is len P2 set over P1 set equal to delta HLV over R 1 over 1. Okay. So these are the two questions, the final question that you have to use in order to solve the problem. So very simple steps that you need to solve. Let's say you need to solve the problem. Find delta HLV of an butane at 10 bar or at 100 Kelvin, or let's say any problem or any at, let's say, 60 centigrade. The pressure is no need, so at 60 Celsius. So what you need to do is, what are the simple steps? The steps are very simple. You just need to plug in the values like so first step is you need to find P set. The second step is you need to find dP set over dt. The third step is you need to find delta VLV. So delta VLV you can see is VV minus VL. So this is the VV, you know how to find. VV is equal to ZRT over P. So you need to go back to chapter 3 where you have to find a Z value, Z vapor root. So depending upon your P set, if your P set is less than 50 bar, you can calculate Z by variable coefficient correlation, by, so VV you can find by cubic or by Lee Kessler or by the variable coefficient. So let's say we have, I can just write down using cubic. So the steps are, so how to find VV. So we have to find beta, Q, alpha TR, and then you can find so for beta we need to find, before than that we need to find TR and PR. Okay. So and then beta, then Q, then beta, then alpha TR, then Q, then Z vapor, and then you can find, yeah, it's using cubic equation. So for VL you need to use racket equation because we are under the dome. Under the dome, this is saturated liquid. So saturated liquid, the best question we can use is racket. So VL will be equal to V set is equal to VC ZC1 minus TR 2 by 7. So this is the then you can, so this is the, you can say, third step. So once you find VL, E, and this is F. So once you find E and F, you can find the delta VLV. Then you can simply plug in the equation. The fourth step is delta HLV equal to T delta VLV dP set over dt. So if you know, so now the difficult thing is, or the leftover or the remaining part is how to find this dp sat over dt and how to find p sat. So for that we have 4 5 questions. So I will discuss in next lecture how we can find the values of p sat and dp sat over dt. Uh, then very simple steps over here. Similarly, if you have delta VLV, you can also find delta LV. It is equal to delta VLV dp sat over dt. So whatever you like you can find. So I will discuss in next lecture how to find the 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 p sat value and the dp sat over dt value. Thank you.